So we are looking to check to see if a given data set is coming from a population that is normal or not. That's why the goal in this section is to use normal probability to access the normality. So suppose that we obtain a simple random sample from a population whose the distribution is not given. We don't know anything about that distribution. It could be normal, it could be not normal, it could be anything. Many of the statistical tests that we will perform on small data sets, the sample size less than 30, require that the population from which the sample is drawn to be normally distributed. Because many of the formula we are going to see in the next few chapters, they require one of the conditions is that the sample size, the sample size when it's less than 30, then we require that the population from which the sample is drawn need to be normally distributed or having a normal bell curve. So up to this point, we have said that a random variable x is normally distributed, or at least approximately normal, provided the histogram of the data is symmetric or the bell shape. So if you kind of wrap that, you should see something like that here, right? Something like that. It's symmetric on both sides. There's the peak at the center, and that divide the curve into half and half, or the bell curve. And this method works well for large data sets, but the shape of the histogram drawn from a small sample of the observations does not always accurately represent the shape of the distribution or the population. And therefore, when the sample size is small, like less than 30, we need additional methods for accessing the normality of a random variable x when we are looking at the sample data. And to do that, we will need a normal probability plot for this section. A normal score is the expected z-score of the data value if the distribution of the random variable were to be normal. So that normal score is just the expected value z-score of the data point if the distribution of the random variable was to be normal. So that's what we call it the normal score. The normal probability plot, this is a graph. We are graphing the observed data on the x-axis and the normal z-score on the y-axis. So you are graphing the x-axis. This is all the observations, all the point that you get, versus the y value. This is the normal z-score. Normal z-score. Okay. So the conclusions, if the sample data is taken from the population that is normally distributed, a normal probability plot will be approximately linear. So if you plot them, you should get something like linear, right? A straight line, maybe going up or maybe sometimes it's going down and so on, but it has to be a linear. And it is difficult to determine whether a normal probability plot is linear enough if the linear correlation coefficients between the expected z-score and the observed data is greater than the critical value of the sample size. Then it is reasonable to conclude that the data could come from a population that is normally distributed. But normally after you graph it, you should be able to tell if that is normal or not. Okay, let's take a look at this one. This is a discussion interpreting a normal probability plot. A random sample of weekly work logs at an automobile repair station was obtained, and the average number of customers served per day was recorded. The data is given below. So maybe this day you have 25 customers that were served, or this day is 24, and so on. Use the provided normal probability plot to access whether the sample could have a confirmed a population that is normally distributed. We have 1, 2, 3, 4, 5. 5, and then we have 1, 2, 3, 4, 5. So 25 value. 25 is less than 30. So we consider that this is a small sample size. Anything less than 30, we consider them to be a small sample size. And then now you are looking for what? You are looking to see if you can have a linear line or not. So we plot the normal probability plot of the sample data, and we get something like this one here, all the point around here. And then we can see that the normal probability plot of the data is approximately linear, because I can draw a linear line going through those points in the direction of the linear line. And therefore we can conclude that the sample data could confirm a population that is normally distributed. Alright, so how do I wrap this one on the TI-84? Okay, so the first thing is we can use TI-84, 83, doesn't matter, 84 or 83, they both works. The first step is you need to enter all the number inside a list. So I go to the second, let's go to start, right? Start, edit. So you want to enter all the value into the list L1. So I'm gonna put 26, 24, the first column, 25, 26, the second column now, and then the third column, 25, 22nd, and then the fourth one, 25, 25, 23, 24, 24, 23, 22, 24, 25, and 24. Okay, we have everything here. Then what we can do, we go to second, start plot, second, start plot. And you want to turn on one of the plot to use. So I use a plot number 1. So I hit that, and then I want to turn it on. And then I'm looking for the normal probability plot. That is the last type here. So you have to move the cursor to the last options, hit enter. Okay. And the data list, this is the list of your data right here. I store them in the list A1, so I put A1. The data access, make sure that when you wrap it, your data access, these value, they have to be on the X value. The Y value is your normal Z-score. Alright, so now I have all the setup correct. Then I can quit. I go to zoom, and then I select the option of number 9, zoom start. And I got that same plot here. So you see that it looks like a linear one, right? It's going up linear. Unless you get something like this, then it's not a linear. This is something like parabola, right? It's obvious that it's not a linear. Linear should be something like going up, going down, something like that. Alright, let's go to the next example. A random sample of 20 undergrad students receiving student loans was obtained, and the amount of their loans in dollars for the year 2011 to 2012 school years were recorded. So this is the amount in thousands of dollars. The data is given below. Determine whether the data could have come from a population that is normally distributed or not. So I have 1, 2, 3, 4, 5. I have 4 rows. So I have 20 data values. 20 is less than 30, and therefore this is considered as a small sample size, and therefore you want to check if this data is coming from a normal population or not. So again, the way we do that is we use again the TI-84 and to enter. So I go to start, go to edit. I already used my L1, so let's just use L2, and then I input everything here to the list of number 2, because the list number 1 I used that for the last example. Now I just enter a new list with all the given value here. (2000) 2200 6200 13200, and then the 4 columns: 14,000, 900, 9100, 750, and then last column, and that is all. And then now I go to what? I go to like second start plot. I can use the same slot plot number 1. Turn on, choose the last options. Now my list is not L1. I just store them in L2. L2 is this right here. So second that to give me L2, and the data asset is still X. And then I have everything. And now I can go to zoom, and I go to option number 9, zoom start, and I check it. Oops, it is a linear or not? Well, you see that on the calculator it is not a linear, right? You can clearly see this is not a linear. This is a curve. It's going up and then going kind of concave up, concave down. So this is not a straight line. This is not a straight line, obviously, and therefore it does not appear to be linear, and therefore the sample data is from a population that is likely not normally distributed. If it's a linear, then you should see a straight line, but this is not. This is not a straight line. This is a curve. So that is a good way to check. And another example. Suppose that 17 randomly selected workers at a detergent factory were tested for exposure to Bacillus subtilis and enzyme by measuring the ratio of forced expiratory volume. So something like that. Now, this is the data. So they ask you, it is reasonable to conclude that the FEV to VC, the ratio, is normally distributed or not. Again, you plot them on the normal probability plot. Then you see that it has a linear, right? A linear pattern. You can see that it's approximately a linear one. So the normal probability plot does appear to be a linear, and therefore the sample data is from a population that is likely to be normally distributed. So it's a good way to check. The last graph is horrible. It won't fit into a linear line, but this one is reasonable to put a straight line in the direction of going through those points and make a linear line. Now we can also use Excel to draw a normal probability plot to check for the answer from this example as well. So there's a few steps for us to consider when we use the Excel to plot the plot. The step number 1 is to arrange the data in ascending order, so from smaller to larger. And then the next step is to compute the f sub I. This is the expression of I minus 0.375 divided by n plus 0.25. And the derivation of this formula is beyond the scope of this class, so we are not going to explore how this formula was derived. And then the index I is just the position of the data value in the order list, and the number n here is just the total number of the observations that you have. And the expected proportion of the observation less than or equal to the I data value is Fi. So Fi is just the expected proportion of the observation less than or equal to that position. And then after we get Fi, we find the z-score corresponding to Fi. And then finally, we plot the observed value on the x-axis. So we are plotting the x-axis will be the observed data versus the expected z-score on the y-axis to get the normal probability plot. So if I have f sub 1, that is equal to z1, or the area to the left of z1 will be f of 1. So the idea behind finding the expected value of z-score is that if the data comes from a normally distributed population, we could predict the area to the left of each data value. And the value of fi, for example, f of 1, represent the expected area to the left of the I observation when the data come from a population that is normally distributed. So for example, f of 1 here is the expected area to the left of the smallest data value, and f of 2 is the expected area to the left of the second smallest data value, and then so on. So once you've determined the f of I, we can find the z-score corresponding to f1, f2, f3, f4, and so on. And the smallest observation in the dataset will be the smallest expected z-score. And the largest observation in the dataset will be the largest expected z-score. And also because of the symmetry of the normal curve, because of the symmetry, the bell curve, the expected z-scores always pair as positive and negative value. Okay, so now let's try this method using Excel to the last example, which is this example right here. Okay, so from this data set we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 of them. So 17 is the small data set, right? Less than 30. So n is 17. So the first steps, when I follow this the fourth step here, I have to arrange the data in ascending order. So the first column here, I'm going to say this is index I, right? And I have 17 of them, right? So I can put like 1, 2, and then I'm just gonna highlight both of them, and then I'm dragging it until 17, because I need 17 input, right, for the index. And then the second column is I need to input the observed value. So I call this column is the observed value. And the observed value here is just what? It's just the data. So I'm gonna put like 0.61, and then I'm just gonna input everything from here to the Excel. And then the next column, you may want to find the Fi. Okay, Fi is what we are looking for in the next column. And then finally, after you get Fi, you wanna find the z-score of that corresponding Fi. So I'm gonna put the expected z-score. Okay, so the first step is you want to put the observed value from the ascending order, so from smallest to largest. So what I'm going to do is I highlight this column, right? I highlight this column and highlight the whole column. Oh, let me do that. Oops. So I highlight everything, here a little bit. All right, and then you can click on data, and you can click on sort the data, and you want from smallest to largest. All right, so click on that. Okay, and then you don't want to mess up the index again. This is, you want to keep them to be the same, so we may want to re-enter it. So put 1, 2. So maybe we sort the data first before you enter the index. All right. Okay. So the index 1 is the smallest value, index 2 the second smallest value, and so on. Alright, so the next thing is we are looking for fi. Fi is equal to the index I. So what I'm doing here is I use a formula, and then on the numerator I get the I, right, the index I, minus 0.375, and then I divide by n. In this case, n is number 17, right? We have 17 total, and plot 0.25, and then you hit enter, and then as you see, if you keep tracking the value down, right, then you get the other fi for the rest of the data point. Just keep doing that, and then all the way to the last one. You can see that this row is equal to the index I, which is 17, minus 0.375 divided by 17 plus 0.25. And that's how you got the fi. Okay, so fi is what you are looking for. And after you find fi, then you're going to find the z-score corresponding to this fi. You're going to find the z-score corresponding to that fi. Okay. So how do I do that? So how do I find the expected value given the area? So the fi right here is the area to the left of the z-score, the expected z-score. So given the area and you want to find back the z-score, then we can use the inverse norm function, right, on Excel here. So I go ahead and use equal sign, and then go to insert, go to formula, insert functions, and then choose statistical and go to the inverse norm functions. So norm.inv, inverse norm, and the probability is just the value of fi, and then the mean is 0 because this is the standard normal distribution. Right, 0 as a standard, and the standard deviation is 1. So that is my expected z-score, and then I just go ahead and track the whole thing down, and then keep doing that. Alright, so that is how you got the expected z-score. Okay, so now the next step is we are going to plot them. So this, the observed value, this is your x, and the expected z-score is your y. Okay, so you're gonna highlight the x column, highlight that. Oops, no. Let me zoom it a little bit. Let me zoom it. Actually, let me zoom it smaller so we can see everything. Okay, right here. So you're gonna highlight all the x first, and then highlight all the y value. Okay, highlight them, and then you're gonna go to insert, and you can use the scatter plots, right, to plot the points. something like that, right? Like this one here. And then from here, maybe you can cut the empty spaces before 0.6 to zoom it, focus on this particular area. So maybe if you click on the horizontal axis and click on right click and format axis, and then the mean value, instead of 0 all the way here, maybe I'll put like 0.5, something like that. Alright, so now you can clearly see this z-score. I mean this probability normal probability plot, and let's compare with what we got earlier. So we see that they are very similar, right? You see that there are two dots right here, which is right here, and then one here, and then it's flow to the bottom up here. So if I place the line, the straight line, then you can kind of see that I'm able to kind of put a linear line going through the direction of those points. And the normal, again, the normal probability plot does appear to be linear. If you see this way, then therefore the sample data is from a population that is likely normally distributed. And again, they are similar in these two graphs here. This is the one generic from the TID4. This is the one from Excel.